Hello and welcome to Open Logic. In this series of videos, we're going to look at writing Testbench using System Verilog and UVM. Having said that, I'll be using System Verilog as base to develop various test components, and along the way, I'll explain how UVM helps in writing these components. I believe it's easier to understand UVM this way than going through UVM code one by one. First thing first, let's start with the design. We're going to use a serializer or a parallel to serial converter. Generally, the design takes in multiple bits in one cycle and send it out bit by bit in multiple cycles. Before we dig into coding, let's try to understand how the design may work. Now there's this thing I call validation mindset. It enables you to figure out about a design even when you don't know much about it. There are certain areas where you can start from, and you'll be surprised how much information you can extract. For example, you can look at clock, reset, and power. For starter, how many clocks are there in the design? If there is only one clock, it takes one cycle to sample in one input data, and it takes 8 cycles to send the output data. In these 8 cycles, do we need to hold the input data constant? Let's say we don't need to do that. Does that mean we can send several input data back to back? We know one input takes 8 cycles to convert, so the pending inputs will have to be stored in the design before they are converted, and that means they are memory elements, and the design therefore is more complicated. For example, how many pending data the design can store? What happens if the memory is full? Now let's look at another possibility. If the design operates at 2 clocks, where the second clock is 8 times faster, then it can convert input data back to back. And now it sounds nice, but again there are complications. 1. Where is the source of the fast clock? There is an upstream component providing the input data. It's reasonable for it to supply this input clock. However, it's not responsible for this output data, and therefore it doesn't make sense for this fast clock to come from the upstream component. Another problem is that if the fast clock comes from the upstream component, this design is pretty much helpless when the fast clock is not synchronized to the slow clock. Therefore, it only makes sense that this fast clock is generated by this design internally, and that should mean the design has capability to synchronize the fast clock to the slow clock. That the fast clock must be exactly 8 times faster than the slow clock, not 7.9 times, not 8.1 times. Else the output may be corrupted. And once again, with 2 clock domains, the design becomes much more complicated. If we extend further, a fast clock consumes more power. One way to reduce power is to use a lower voltage for the fast clock. That creates a 2 power domains design, and it requires level shifter to interface between the 2 power domains. Well, we can go on and on, but the general idea is we can extract many design information by simply looking at its clock domains. This kind of skill set will allow us to plan a thorough validation for the design. Now let's look at the design code. First stop, the design pins or the design interface and its behavior. And this is a very important aspect. We must be able to communicate the design behavior by using the pins. This behavior is a specification. It forms a contract between designer and the user. It allows user to create other components that can integrate with this design. Alright, let's begin. This is an input clock to the design. This is an input reset. And these pins are used for data conversion, and these pins are used for design configuration. And this is how the clock behaves. And this is an asynchronous reset. It is asserted at the beginning to put the design into a known state. And this is how we can send the input data. We need to qualify it with a valid signal. If the valid signal is low, the design would not take in the input data, and therefore the input data value is don't care. Output data on reset is 0. Upon sampling of an input, the conversion begins immediately, and the output is sent out bit by bit, cycle by cycle. There is an output valid signal. It qualifies the output bit stream. Now let's switch to configuration. There is only one configuration, which is the size of conversion. The default value is 7 upon reset. To set the size to a new value, we need to assert the right signal along with a new size value. The configured size value is always visible at the output CR size here. The size is value plus 1. If it's 7, it means to convert to 7 plus 1 bit. Before we continue, in reality, a design can have many configuration registers, or configuration registers that don't have individual pin at the design level, because that would be very expensive and not scalable. Imagine adding a register or removing a redundant one. Usually, all config registers share a common interface where an address is provided to select which register to access. This reduces pins on the design level and allows flexibility in adding or removing config registers. However, I only have one configuration in this design, so I use a much simpler interface. Another note, if you pay attention to the pin names, input is denoted with a prefix I and output is denoted with a prefix O. This helps to promote code readability. One more note, looking at the pin's behavior without having to look at the internal signals, this is commonly known as a black box view. Alright, let's combine all signals and understand it as a whole. Let's say we never set a new size. The size is the default reset value 7. At this clock, an input data appears, and at this clock, the input data is taken in, and the conversion starts right away. The size value is 7, effectively the number of bits converted is 7 plus 1. After 8 clocks, all bits are sent out. Now let's say we set the size to 5. What do you think will happen? Well, this is a bit of a gray area, but very likely the behavior is the same as before where all 8 bits are converted. It depends on whether the design uses the value from the input CR size or from the output CR size. And very likely it uses the output signal, because an input signal can be disruptive during a multi-cycles operation. Anyway, in many designs, configuration phase is separated from data transfer. Always perform configuration first, followed by data transfer. In this case, if we delay the data transfer 1 clock, it will use the new size value 5 and therefore 6 bits are converted. Now, one very interesting question. To what extent do we want to validate the design? Follow the design specification exactly or more than that? The answer is unfortunately most likely the second. In many ways, a design specification is subjected to interpretation and more often than not is incomplete. If we pretend this timing diagram here is the spec, we need to figure out other use cases beyond this spec. For example, can we send a second data while the first one is still in progress? There are 3 possibilities. One is the second data is stored in the design pending conversion, and that requires memory. Another one is that the second data is ignored, which is generally bad. The third one is that the previous data is overridden. A new conversion starts right away, which is also bad. Whether it's truly bad or not, it depends on customer requirement. Another example is, can we set a new size value at the middle of a conversion? It's the same question, will the new size be used on the next data, or will the new size be effective immediately? At the end of the day, we do not want customers to see bugs in the design. So we have to ensure the spec is clear and validation scope has to cover all possible scenarios. Now let's look at the internal code. It's a simple design, but there are still too many lines, so I'll show part by part. This first part handles the configuration. It uses clock and reset in the sensitivity list. If it's being reset, the configuration register size is set to 7. In the else statement, if a write is being performed, the output CR size gets the new value, else it keeps the old value. This part is handling the data conversion. We need some extra signals. Data latch is to store the input data so that the next 8 cycles, output data can use this stored data and not depending on input data, which may change. The signal position is to indicate which bit to send out from the data latch. The effective CR size is to capture the size to use in upcoming conversion. In this always block, this part is to handle the reset phase. While not in reset, this part is to handle ongoing conversion, this part is to handle newly detected conversion, and this part is to handle idling phase. Upon reset, basically all signals are driven to 0. Pretty simple. And while the design is idling without any input data, it's the same as the reset phase. When the new data presents, the data is latched, then the output data immediately drives bit 0 and output data values is set to 1. The effective CR size captures the size and the position is set to 1, meaning to send bit 1 at the next clock. While there is an ongoing conversion, output data will now get the bit from data latched by using the position value. Output data valid remains 1, data latched and effective CR size remained unchanged. The interesting code is updating the position. Generally, the position keeps on incrementing until it has finished the conversion, at which point it resets to 0. It decides that the conversion is finished based on the effective CR size, where position is equal to effective CR size. After position resets to 0, it will no longer enter this if statement. It will only enter this else if statement if there is a new input data, or the else statement if there is no input data. And now we can combine all signals and view the behavior. If we include internal signals inside the module, this is generally known as a whitebox view. It gives us a better understanding of a design, but it is generally recommended not to use the internal signals in validation. For one, they are not included in specification and therefore they can change. For example, the code here uses behavioral modeling. Maybe someday a designer decides to code using primitive gates in a structural manner, trying to reduce size of the design or any other reasons. The internal signals may be removed or renamed, or their behavior is no longer the same. Regardless of how it is done, the interface behavior cannot be violated and is always reliable. Alright, that's it for this round. Next, we will look into writing directed test. Before we go, if you like this video, don't forget to like, share and subscribe.